All right, 2.7. We're looking at inverse functions, horizontal line tests, one-to-one functions. All these things go together. Okay, so an inverse function is something that takes the output of one function and changes it back to its original input. Okay? So an inverse function, let's say we're given just some graph of a function. Let's say we have a point over here at -4, 0, and then we have another point up here at 0, 5, and then we have another point here at 2, 6, and then let's say we got another one here at 4, 8. Let this go up a little higher. 8. We said this was 5, and this was 6. 0, 5 is over here. All right, so just just a line graph. It's a function, right? It fits the definition of a function. So what an inverse function does is it takes the output. So we don't know exactly the algebra of this function, right? We just know it's a function. F of x is y. So what the inverse function does is it takes the original input of x. Okay, in this case, the original input is -4. The output is 0. What the inverse function does is take that output of 0 and change it back to its input of -4. So if you were asked to graph the inverse of this function, see if I got a different color marker here. Instead of -4, 0 being on the graph, 0, -4 is on the graph. Instead of 0, 5 being on the graph, 5, 0 is on the graph. Instead of 2, 6 being on the graph, 6, 2 is on the graph. And instead of 4, 8 being on the graph, 8, 4 is on the graph. So notice, I mean, I probably didn't draw this quite, perfectly, but if you did this on a more exact graph, the inverse function is always going to be a reflection about this line, y equals x. Remember, we looked at this as one of our main functions when we did the transformations, right? Just that line that goes through diagonally. So if I connect these, this should look something like this one. We said this was 0, 5, then 4, 0, -4, and 5, and then that. My picture isn't perfect, but you can see it's sort of, if it was on a perfect graph, it would be a reflection about this line. So labeling the points makes it clear. This is 0, -4. This is 5, 0. This is 6, 2. And this is 8, 4. So notice we just changed 4, 8 to 8, 4, 2, 6 to 6, 2, 0, 5 to 5, 0, -4, 0 to 0, -4. And we get a mirror image about this line, y equals x. That's going to happen for any inverse function. So what we want to be able to do in this section is a couple of things. We want to determine whether two functions are inverses of one another, and we want to be able to find the inverse of one given function. So let's look at the first case first. We look at number 4 on page 309. We are given two functions, 4x plus 9 and x minus 9 over 4. Okay, and the question here is, are these inverse functions? But does the output of one function, when put into the other function, give you back the original input? So we're going to use what we just learned about composition to answer this question. Right? So given these two functions, the question is, are they inverses of one another? All right, so to answer that, we're going to compose in both directions. If I put this function, this output, right, this is the output from the f function. If I take that output from the f function and put it into the g function, I should get back x. Right? That's what we were saying over here. And if I put this output into this function, I should get back x, right? Because it goes both ways. So let's see. So I'm going to find f of g of x. All right, I'll write it all out here again, all the different ways we look at it. You don't have to write both of these. One of them suffices. I like this one, but I'll put this one here just to show. And then we're going to put that g of x function as the input to the f function. So the f function says take the input, multiply it by 4, and add 9 to it. So the input is this. We're multiplying that input by 4 and adding 9. And notice here, the 4's cancel out. We're left with x minus 9 plus 9, so we do get x. So that's half of our proof. So we're asked to show or prove that these two are inverses of one another. So if that didn't equal x, you're done. You can say no, they're not inverses, because if one way doesn't work, then they're not inverses. But if this one is x, then we go to the other direction and find g of f of x. All right, so now f of x becomes the input to the g function. So the f function is 4x plus 9. That becomes the input. The g function says take that input, subtract 9 from it, and divide the result by 4. So we take that input of 4x plus 9, we subtract 9 from it, and we divide by 4. And notice the 9's cancel out. 4x over 4 does give us the x that we wanted to see. So yes, these are inverses because of that. Okay. Now if either one of these answers is anything other than x, then no, they're not inverses of one another. So that's how you determine if two functions are inverses. So the next thing we want to look at is, given one function, how do we find its inverse? So let's look at number 18. Number 18 on page 309. All right, so now we're given one function. Given f of x is x cubed minus 1. And we're asked to find its inverse. So what we want to do here to be complete is we'll go through the process of finding the inverse, and then when we find it, to prove that we're right, we'll come back to do the same proof that we just did over here. Okay, so now the question is find the inverse. All right, so you take the original function, rewrite it with a y. Okay, remember we said f of x and y are the same thing, right? Y is the output of a function, f of x is the output of a function. It's just two different ways of saying the same thing. So rewrite it in terms of y. So rewrite with a y. So now, to find the inverse, what we're going to do is we're going to switch the x's and y's. Okay, so first step, rewrite with a y. Second step, switch x's and y's. Everywhere you see an x, put a y. Everywhere you see a y, put an x. So y becomes x becomes y. All right, so we switch the x's and y's. Now we're just going to solve for y. All right, so we got y cubed over there on the right-hand side. We want to isolate that term, so we'll add 1 to both sides. And then we have that y cubed, so we have to recall our properties of exponents and ask ourselves, what do we have to raise this to get that to be a 1? Hopefully we remember our property that says raising something to a second exponent requires multiplying those exponents together. So really we're saying, what do we multiply 3 by to get 1, which is 1/3. So now we're going to raise both sides to the 1/3 power, and y cubed raised to the 1/3 using this is going to give us y to the first. We'll come over here and say y to the first equals x plus 1 to the 1/3. And remembering our fractional exponents, this is the same as saying the cube root of x plus 1. Either one of these is acceptable. And that is our inverse function. So inverse function of x is denoted with this -1. Now it's not an exponent on the function, that's a way of writing the inverse function. So that is the notation for an inverse function, is this f, which looks like a -1 exponent, but it's not when it's on a function. It means the inverse function. All right, so now let's check and see if we got it right. All right, so now we're saying that I have two functions, right? I have this function, f of x, and I came up with what I hope is the correct inverse function. So let's check that by using the technique we just used a few minutes ago. So to prove that this is correct, or to check our answer, we want to find f of, again, what we're hoping is the inverse. I'm labeling it as the inverse. All right, so what we found over here, let's use, it doesn't matter which form you use, I'll use the x plus 1 to the 1/3. You could use the cube root if you choose. Generally, in an algebra class, fractional exponents are preferable to radicals. They're easier to work with, so it's a good habit to get into using fractional exponents instead of radicals. Okay, so anyway, we have the f function tells us take the input, raise it to the 3rd power, and subtract 1. So we're going to take the input of x plus 1 to the 1/3, raise that whole thing to the 3rd power, and subtract 1. And notice the 1/3 times 3 is going to give us x plus 1 to the 1st power. And then we're going to subtract 1, and we get what we hoped to see on the first half of the check. Right? Now that doesn't prove it yet, right? Remember, we got to go in the other direction also. But that gives us a good feeling that we probably are on the right track. So now we want to go in the other direction, the f inverse of f of x. Okay, so now we're going in the other direction. Here we took f of f inverse. Here we're taking f inverse of f. So now the f function was x cubed minus 1. So that becomes the input to our new function, which we had over here as x plus 1 to the 1/3. So the input is x cubed minus 1. That's the input. plus 1, all of that raised to the 1/3. Right? X plus 1 to the 1/3. X plus 1, all of that raised to the 1/3. And we can see here, within the parentheses, minus 1 plus 1 is going to leave us with x cubed raised to the 1/3 more x. So that shows that we did in fact do this step right, these steps right, and we got the correct inverse function, and now we know without any doubt that it is in fact correct because we checked it using the method we started out the section with. All right, so those are the two things you want to know how to do concerning inverse functions. Given two functions, be able to determine whether they are inverses of one another, or given one function, be able to come up with its inverse. Now, you're not always going to be able to come up with an inverse. Not every function has an inverse. And that's where this horizontal line test and one-to-one functions come up. So the horizontal line test acts very similarly to what we discussed earlier with functions, the vertical line test. So remember, the vertical line test told us whether a graph of a relation was a function or not. The horizontal line test tells us whether a function has an inverse, whether a function has an inverse or not. Okay, and if a function has an inverse, it is called a one-to-one function. So remember, going back to the definition of a function, each individual x could have at most one y output. But remember, let's look at x squared. If y is x squared, we know what that graph looks like, right? Parabola with its vertex at the origin. Now this passes the vertical line test. Remember, you said the way to pass is that it only can pass through at least one, at most one point in the graph. But it doesn't pass a horizontal line test. Right? This passes the vertical line test. So it is a function. But it does not pass the horizontal line test. So it's not a one-to-one function. And if it's not a one-to-one function, it has no inverse. Okay, so this is what you want to notice from horizontal line test. It tells you whether a function has an inverse. Now, if we tried to find this inverse, right, if we went through our method here, and we said y equals x squared, and then we changed and tried to solve for y, we would get not a function, right? That doesn't fit the definition of a function. Because 1x gives me, one certain x. If I solve for this, this is plus and minus x, which doesn't fit the definition of a function, right? Y equals x squared, we switch the x's and y's, we solve for y, the square root, right? Plus and minus the square root of x. So each x, when I put one x in, I get two outputs, which doesn't fit the definition of a function. So it does not have an inverse function. It does not pass the horizontal line test, but it is a function, right? So that's the difference between vertical line test and horizontal line test. So a one-to-one function, let's look at an example of a one-to-one function. So notice this is not one-to-one because two inputs, say -2 and 2, they both have the same output of 4, right? That's not one-to-one. Remember, each input can have at most one output to be a function. But to be a one-to-one function, then it goes in the x direction also. Each x, two x's can't have the same output. These two x's and an infinite number of other pairs of x's have the same output here, therefore it's not a one-to-one function. If we look at something like x cubed, then we see a one-to-one function. Right, that passes both the vertical line test and the horizontal line test. So this is one-to-one and does have an inverse. Okay, if we try to find this inverse, we switch the x's and y's, and when we take a cube root, we don't have to take a plus or minus, right? Because it's an odd number, so x to the 1/3, that's the inverse function to y to the x cubed. The inverse function is x to the 1/3. Okay, so horizontal line test, one-to-oneness are really the same coin, two sides of the same coin. So let's see what else we need to look at here, if anything. 2.7, we covered inverses, finding inverses, horizontal line test, one-to-one function, finding the inverse. Okay, we're good.